Well, let's talk about the motion of a system of particles and how momentum relates to this. And we're going to talk about external forces on a system of particles and internal. If I've got, what do we mean by system of particles? A system is just an object or a group of objects that we've decided to focus on. And so I'm just going to draw a bunch of little particles here in two-dimensional space. And each particle has its own mass. And maybe it's moving in its own direction. We use systems of particles analysis like this to try to understand things like ideal gases in chemistry. Or astronomers use this, to look at star clusters and so on. So it's a very, very common thing to do, to look at a system of moving particles. And so the first thing we can say, well, where is the center of mass of the system? And remember what we said about the center of mass of the system. It's 1 over the total mass times the summation of each little particle's position times each little particle's mass. So this was how we expressed these, and you can, could you guys, I don't know what you guys are doing, but it's distracting. If you could, so you can use this formula in both, and you would break this down into its x and its y components and figure out where the center of mass is of this thing. But here's a question. If this is a system of particles that are moving, is the center of mass moving of the system?
Like the whole system is moving.
Or is it at rest? I could have a system of particles where the center of mass is not changing for the particles, even though the particles are moving.
Wait, no, what do you mean by moving? You mean like they're all kind of like aggregate, like moving in one direction?
Exactly. What if, so what I want to do is I want to look at a system of particles where the particles each have their own individual motion. But what's true about the center of mass of the system? Is it moving or not? Well, if this represents the position of the center of mass, then what can I do to find the velocity of the center of mass? What do I do to position to find the velocity?
Like derive it?
I take the derivative, the time derivative of it. So let's take a look at this. This is 1 over m times, I'm going to switch the order. It doesn't matter which one you put first, but let's say the masses of these particles is not changing with time. So, oops, I didn't mean to do that. M1 R1 plus M2 R2 plus ... plus MN RN. Okay? So this represents the center of mass of the system. And what I'm going to do is I'm going to take the time derivative of both sides. Well, if this is my system, and I'm going to say, okay, I'm not going to add or subtract any mass from my system. My system, the mass of my system is not going to change with time. Okay, does that make sense? So this is just 1 over m. This is the total mass. This doesn't change with time. So it's just a constant. Okay, so it just stays there. I mean, you don't even bother with the product rule. And you don't even bother with the product rule inside the parentheses here. These individual masses, we're just going to say, let's assume that they stay constant. Which is a very good assumption for almost every application of this. So let's take the derivative of this with respect to time. Well, the derivative of the position of the center of mass with respect to time is called the velocity of the center of mass. And this is just going to be 1 over the total mass. Okay, and then we got to take the derivative of these guys. Well, let's take the derivative of this. I mean, this is really pretty simple. M1 is a constant, but I have dr1. Well, the derivative of this is just dr1 dt, but what is dr1 dt? That is that's the velocity of object 1. Okay, oops. So that's what we get. Okay? Does that make sense to everybody? All right. Well, now this gives us something kind of interesting. Let's multiply both sides by the total mass here. So I have the total mass times the velocity of the center of mass equals this stuff right here. I'm not going to rewrite it, just write it like that. Now, what is this? What is mass times velocity defined to be? I mean, we're in chapter 9. It's momentum. Now, this is really kind of cool. This represents the momentum of the center of mass. The momentum of the center of mass is equal to the sum of, and what is this? This is the momentum of object 1, this is the momentum of object 2. It's just the sum of the momentum of each particle. So if I want to know what's the momentum of the system of particles, now this makes sense. What's the momentum of the whole system? Well, you just add the momentum of each thing. But that will be the momentum of the center of mass of the system. So let's say for the system I drew, let's say like maybe this is a really big one or something, I don't know. Let's put the center of mass right there. The momentum of my system of particles, might be kind of drifting up into the right a little bit. So these particles, even though each individual one has its own momentum, if you add them all up, the whole thing's kind of maybe drifting up into the right. Or maybe when you add all these up, you get 0. That's all right. Now, what do you get when you take the derivative of momentum? The time derivative of momentum. Yeah, well, no, it's not impulse. What do you get when you take it? You get force. Yeah. Okay. So let's take the time derivative of, well, we can take the time derivative of this. Let's take the derivative of that. Well, let's again assume that the mass of my system is staying constant. So this is just a constant. What's the derivative, time derivative of velocity? Acceleration. So if I take the time derivative of this whole thing, what I get is mass times acceleration, which is the force, the net force acting on the object, or acting on the system. And that's going to be equal to the sum of all of the derivative of all of these guys. Well, it's the net force on object 1, and the net force on object 2, the net force on object 3. Okay. And so now, what if there is no net force? What if my system is isolated from the universe? So we're not exchanging mass with the rest of the universe, and there's no net outside force acting on my system of particles. What's going to be true about this net force? It's going to be 0. Now, the derivative of what is equal to 0? Any constant. So what that's saying is that if there is no net outside force acting on my system of particles, the momentum of my system of particles will be constant. Okay? And this is just, we're doing the same thing that we did for individual particles. We're just saying that, hey, the momentum will be constant with time if there's no net outside force acting. But what if there is a net force acting on my system of particles? Well, that will result in the change in momentum of each, when I sum them up, of each individual little particle. Now, what this does is that when you're analyzing a large system of complicated particles that are all moving, let's say you're an astronomer, and you want to analyze the motion of a cluster of stars. There might be hundreds of thousands of stars in this cluster. And if you want to understand the effect of other clusters on it, or maybe there's a massive black hole nearby and you want to understand its motion, well, it's pretty difficult to treat that cluster of stars as 100,000 different particles, because that's just too much work. But what does this analysis allow me to do?
What is like one thing?
It allows us to treat it like one thing. Exactly right. So what it does, say you have the system of particles, let's just treat it like it's all one particle concentrated at that center of mass. And then we can say, all right, if there's a net outside force acting on my system, then I can apply that to my center of mass location and do that. Now, if I want to understand the motion of one of the particles, then I have to analyze it all by itself. But if I want to understand the motion of the system of particles as a group, I can treat them as, like that. So now here's a really interesting example of that, and that is an exploding projectile. Okay, which is kind of morbid. But let's say I've got a flat plane like this, and I launch a projectile. And this projectile has a certain mass m, I'll give it big M, and here's its initial velocity. Now let's suppose that it doesn't explode. You know what the trajectory of this particle will look like, right? It's going to be a parabola in the sky. Let's assume air resistance is negligible. And we dealt with this, in chapter 4, I think. You have projectile motion. But let's suppose when you get right here in the flight, it's got a fuse in it, and it explodes into thousands of little pieces of shrapnel. And so when you think about what happens when you have a shell that explodes, inside that shell you have forces that are blowing it apart in all different directions. Let's imagine that it's a sphere. Inside the sphere is some gunpowder or something like that. And when that gunpowder explodes, it pushes out in all different directions, right? And so you'll have little pieces of shrapnel. Okay, this could be a grenade or whatever, any kind of a bomb. Now, these pieces are pushed away. But remember that for every force, there's an equal and opposite force on another object, right? So if I looked at at this thing as just if I look at the whole thing as my system, each little part of this exploding shell is all part of my system, well, then these forces are all internal to my system. So in other words, if this part gets pushed this way, there's another part that's getting pushed in equal and opposite way, Newton's third law. For every force on one object, there must be an equal and opposite force on another object. So there is no net force on my system as a result of the explosion. Well, what does that mean? That means, now there is a net force acting on my system in this problem. What is the net force acting on my system? Gravity. But, so, in fact, if it doesn't explode, it'll go right, like, and land right there. But what if it explodes? Well, you're gonna have parts thrown in all different directions. But what's true about the center of mass? The center of mass is not, the trajectory of the center of mass of the system is not going to be affected by the explosion. The center of mass will land right here. Now, does that mean that there's any shrapnel there? Not necessarily. I could have a piece of shrapnel here, 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 and here. Let's say it's a weird thing and it's all in 2 dimensions, okay? But obviously it's in 3 dimensions. But where all the pieces land, this one might go and land over here, and this one might go land here, and this one will land here, and this one will land here, and this piece will land here. This part will be blown all the way over here, and like this. So all these pieces are going to be scattered. But guess what happens when I measure the center of mass of all these particles?
It'll be at the other end of the problem.
It'll be right there, right at the end of our rainbow. Okay? Well, actually, I think a rainbow is a circle, not a parabola, so that's not a good analogy. But anyway, that's where it will be. Another more peaceful application of this, and a little simpler actually, if you have a system of particles that's represented by 2 train cars. The only thing we like more than crates are train boxcars. All right, physicists anyway. So here's a train, and we'll call this particle 1. There's a bigger one. It's got more mass. It's got filled with coal or something. And this is particle 2. Now the center of mass of my system will be right here. Now let's say this one is moving, let's say this one's moving like this, and this one's moving like this. Okay, those are the initial velocities. So I think you can see here that the center of mass, let's try to draw a little cartoon in our heads and visualize this. These guys are going to be moving to the right, but 1 is catching up with 2, isn't it? So what's the center of mass going to be doing? It's going to be moving along with the 2 trains, but as 1 catches up to 2, the center of mass is catching up to 2 until they connect. But let's say that they collide and connect to each other. What's true about the velocity of the center of mass before the collision versus after the collision? It's going to stay the same. The velocity of the center of mass is not affected by the collision of the two cars, whether they stick together or not. So I think that there's a problem in an example problem in the book where you have this is one of the last polar bears, unfortunately.
Oh man.
Yeah, and so you want to you tranquilize the polar bear, and you're out there on the ice. You're a field scientist, and you want to measure or come up with the idea of how much mass does this polar bear have. So, well, if you know the mass of the scientist, and you know kind of where the center of mass is, you can actually pull each other. You can pull, and by measuring how much you slide compared to how much the polar bear slides, and you know where the center of mass of your system is, you can figure out what the mass of the polar bear is. That's what this example is about. So you'll be dealing with that. So lots of what's that?
How much of the center of mass and not how much they weigh?
Well,
Eyeball it.
the mass and the weight are related by g, and so you can figure it out. But also, you can think of a diver or a gymnast as being a system of particles, an extended object, and they will always rotate about their center of mass. Now, I'm going to show you a video of that, and then I actually have a little demo I'm going to show you, but I can't do that on the camera, so that's all for this.